So a Lie group. It is something, a set which has two structures. These two structures are, it is a manifold and it is a group. These two structures should be related in the following way. So G is my, some chalk. This maybe a problem. No, I see. So it is G, traditional notation for a group. And as a group it has multiplication, which can be regarded as a map of G times G into G, and the inversion. I mean, this is G inverse and this. But also it is a manifold. So both maps should be smooth. And this is a definition of a Lie group. Questions about this? My first and my main definition. Questions about this? Examples. Maybe you have some examples. Can you imagine such a thing? Say, straight line, R. It has a manifold structure, right? It has a manifold structure, certainly. And also, the addition operation, which is mu in this case. And the map, if G is R, this map, R cross R, which is plane, and the map of R times R into R is x, y goes to x plus y. Certainly this is a smooth map, very much. Certainly we can take Rn Euclidean space away in dimension again with the addition operation. It is the first example of a Lie group. Very simple, not very interesting. One more. So circle, S1. It is a manifold, one-dimensional manifold, and the multiplication, addition again, addition operation, usual addition of angles. These two groups are commutative. We can consider matrices. N cross N matrices with non-zero invertible with non-zero determinant. And the set of these matrices is denoted as GL, N, and then the denotation for the field. In our case, R or C. Usual matrix multiplication makes it a group, and this group has is not commutative. It is a manifold. Why? Because actually GL and R, GL and C similarly, is an open set in the space of all matrices. Space of dimension n squared. So GL and R, similarly for C, is an open set in the space of all my matrices, which is Rn squared. Open set in Euclidean space is a manifold, certainly, and the multiplication operation, inversion, both of them, certainly are smooth maps. Manifolds have dimensions. So this group has dimension n squared, and 2n squared if you consider complex matrices. Then S and R or S non C. Same as before, but now we consider matrices whose determinant is 1. The multiplication is the same, but I say that it is also a manifold. Say S, L, and R has a natural manifold structure. 1. Why? Sure. There is a function on the set of all matrices, the determinant. It is a very much smooth function, actually algebraic. Smooth function. And S, L, and R is the set when this function is equal to 1. To be one equation determines a part of this n squared dimensional space. If you want that this space is a manifold, we need some additional condition. You remember, equation determines f is equal to, say, 0 or 1, determines a manifold if at every point of this set where this function is 0 or 1, at least one partial derivative for this function is not 0. You understand, the gradient is non-zero vector. This requires certainly some additional checking, which can be easily done because our function is very very explicit. The dimensions is n squared minus 1 here, and twice this here. To this, I can add orthogonal matrices and unitary matrices. Do you know what a unitary matrix is? Orthogonal matrix is a matrix whose inverse is equal to its transponent, and unitary matrix is the same also with the bar operation. So the inverse of a matrix is equal to the bar of its transponent. Do you know dimensions? Well, certainly there are manifolds, and also this requires some checking, which I didn't do, but if they are manifolds, they have dimensions. Dimension of this. Ever heard of that? What is the dimension of the manifold of all orthogonal n cross n orthogonal matrix? Say O2 is the same as well, at least this component, there's two components, but each component is a circle. Dimension is 1 if for 2. In general, the dimension is n. The dimension of this is n squared, believe it or not. So I will not make this computation, but you can check this. Also, I want to mention, to make this list complete, the groups SON and SUN. What are they? This is the intersections of the groups in the examples 4 and 5. So we consider orthogonal matrices, but we specify that the determinant is 1. For the orthogonal matrix, the determinant is plus minus 1. And actually, ON as a manifold is disconnected. Consists of two components. SON is the component which contains the identity matrix. SUN. This is the group of unitary matrices with the determinant 1. If I forget to say this, what is the determinant of a unitary matrix? It is a complex number whose absolute value is 1. otherwise arbitrary. So actually, when we say that the determinant is 1, it is a condition more essential than just a component. By the way, UN, the group UN is connected, so no components. As UN has dimension 1 less than UN because of this condition, which actually affects its dimension. It becomes 1 less. So dimension here is n squared minus 1. And there are some errors in my notes, which certainly I will correct in my next mailing to you. I have more than this now. This is actually, there are Lie groups which are called classical Lie groups. Not only this, something else. But this will be, at least for some time, the main source of our examples. Yes, Claudia?
Are orthogonal groups complex or real?
These groups are real.
Okay.
But certainly you can write O and C. Complex orthogonal matrices. This is the same as orthogonal matrices, only simply the matrices are complex, and we do not apply the bar operation. So O and C consists of complex n cross n matrices whose inverse is equal to the transponent. It is also a group and not the same as unitary group. There exists such a thing in geometry. I didn't want to mention it, but I see that you will not let me miss anything. There is a huge theory of complex manifolds. And this UN is not a complex manifold. N squared, by the way, believe me, can be odd, if n is odd. So this cannot be a complex manifold. This is a complex manifold. So these groups are very much different. This group is compact. This is not. So many different things which make them different. I didn't want to mention this. There are some other group. And I thank you for not asking me about symplectic groups, but at some moment we will have to consider that. As usual, when we consider examples, it is not sufficient just to list some examples. It is reasonable to have different operations which produce Lie groups from Lie groups. There are 3 obvious ones, or maybe better to say 2 obvious, 2 very obvious, and one just simply obvious one. Very obvious ones. Component. So operations. The usual notation G sub 0. If G is not connected, then we can consider the connected component. By the way, the word connected, certainly it has some topological meaning, but I will mean path connected. So connected means that every 2 point can be joined by a path which for manifolds is the same. There are examples of nested topological spaces which are maybe not path connected being connected, but this for manifolds, no, this is simply technically I will mean the connectedness in the case of path connected, sense of path connectedness. So G0 is the component of the identity element. By the way, identity element I prefer to denote as lowercase e. E, the identity element in the group G, and G0 is the component which contains E. And I say that it is a subgroup. Is it really so? Maybe. So my question is what? If I have two elements in G0 in the component of the unity, can I be sure that their product also belongs to the component of unity? Or it is too much? What do you think about that? You think yes, and I think yes. And I can say this in two different ways. For those of you who prefer algebra, you will more like the first way, and for geometers, like many people, including myself, the second way will be more better understandable. So first of all, we have a map, G, right? It is mu, multiplication. In particular, the same mu can be applied to G0 times G0. This is connected, right? And the image is connected. Image of connected space, path connected, is certainly connected. Now, it takes E is in G0. So this is in G0 times G0. So this belongs to the image. So we see that the image of mu of G0 times G0 should lie in G0. Actually should be equal to G0 by obvious reason, but I can now say that yes, G0 is a subgroup. A different way to say the same is the following. So this now is the picture. This is E. This is G and this is H. And suppose that they both belong to G0. There are paths which join E with G, E with H. Paths are parameterized curves, parameter from 0 to 1. So if you take the points, let me say this path be S1 and this path be S2. S1 of T, S2 of T, and multiply them. So this is S1 of T times S2 of T. Then you get a path which joins E with GH. When T is 0, it is E. When T is 1, it is GH. This is the other way to say the same. So G0 component. In our examples, I can only say that the component of ON is SON. By the way, the group GL and R also is not connected. The determinant is not 0, that's okay, but it may be positive or negative. And these are two components. You can consider only matrices with positive determinants. The usual notation GL plus of NR, I didn't write it, but it is a subgroup of GL and R, which is the component. But in general, if we have a disconnected Lie group, we can find the component. By the way, it is a normal subgroup. It is a normal subgroup. And the quotient, the group of components. Well, this is maybe too much. So this is one thing. The obvious thing number one. The obvious thing number two. We can take products. If we have two Lie groups, G1 and G2. Then the product G1 times G2 is also a group and a manifold, and everything is okay. So we can take products of Lie groups, which immediately gives many examples, new examples obtained from existing examples. Okay? Now, just to extend our terminology, subgroups. Lie subgroups. Believe me, with all, how to say, easiness of this notion, still, there are different definitions, not equivalent to each other. And in some cases, it's not very clear how to define a Lie subgroup. I use the following definition. A Lie subgroup, we have a manifold, G, then a submanifold, which I suppose to be a closed subset of this manifold. And also it is a subgroup. So the following condition, a subgroup of G, which is closed with respect to topology. Moreover, with respect to topology, it is a submanifold of some dimension, certainly containing E, because it's a subgroup. Then it is a subgroup in the usual sense. And this is the definition which I'm going to use. Okay? For example, Q, the set of rational numbers, is a subgroup of the group R. And I do not count it as a Lie subgroup, because it is not closed. There is a very funny theorem, which I'm going to prove eventually, but not today. Today I have 6 more minutes. Believe or not, I know, maybe some of you do not know this. If you have a Lie group and a subgroup which is just closed with respect to topology, nothing else, closed subset subgroup, then it is a Lie subgroup. Then it has to be a submanifold. Can you imagine this? Certainly a closed subset of a manifold shouldn't be a manifold. Very clear. But if it is a subgroup, then it's a manifold. It is called Cartan's theorem, which doesn't say much about the theorem, because Cartan actually proved almost everything here. But this particular theorem, by reasons which are not known to me, is called in books Cartan's theorem. I will give you a proof, and it is already in the notes which I mailed to you. So subgroups. There are some subgroups which you can immediately detect. For example, suppose that you have group ON. Well, SON, because I prefer to have kind of group. Or well, not important. Can you name some subgroups of it? Hmm? Are you sure that the product of two symmetric matrices is symmetric? I'm not so sure. I say ON. Orthogonal matrices. What are subgroups? Can you find some subgroups? Hmm? Please say just louder.
Is it upper triangular?
Orthogonal matrices. I'm not sure that they can be upper triangle. Yes, diagonal, yes. Diagonal, yes. It is an example, but this is not the most interesting example. Please say, for example, that ON minus 1 is a subgroup of ON. Thank you for this. ON minus 2 also. But also, for example, you have O7. Then you have a subgroup O4 times O3. Just consider the block diagonal matrices with the blocks of dimension 4 and 3. And this is also certainly this not only for 7, 4, and 3. Actually, if n is equal to n1 plus nk, then the group On contains this product. Again, block diagonal matrices. Okay? If you replace O by SO everywhere, it will be the same. Or if you don't like O or SO, you can write U. SU is also okay. So there are many examples like this. There are more interesting examples. For example, UN, believe or not, is contained in O to N. Right? On, by the way, is contained in UN. If the unitary matrix is real, then it is orthogonal. So there are such inclusions. On is included in UN, and UN is a subgroup of O to N. Lots of examples. Now, before I finish, I have 56 seconds to finish. I want to say that there is also a topological construction, which I'm going to consider at the beginning of the next lecture. Covering. Do you know what a covering is? I don't mind, but I need to understand how much you need to say about this. You can look through my notes. It is written in a footnote, everything which is needed for coverings. But if you have a cover, if you have a Lie group, and any manifold which covers it, then it has this manifold, covering manifold, has a natural structure of a Lie group. It becomes unique if you choose the identity element. When you have a covering, then the inverse image of every element of covered manifold consists of some amount of points. You choose one of them and say this will be the identity element. Then there exists a unique structure of a Lie group on the covering, says that the projection of the covering onto the manifold becomes a homomorphism. The notion of Lie homomorphism certainly is very natural, and also I will have to define this next time. Now I have to finish. Thank you for coming. I hope that some of you will come next time.